to run a mile in minutes, seconds, minutes. I'm going to go minutes. And the temperature, the body temperature after running 1 mile. All right, so I'm totally making up the data, but
this is an example of what we're.
yeah, exactly. And again, you don't have to collect the data yourself. You can just find an internet resource and go from there. But my objective in this one is to say that the faster a person completes a 1 mile run, the more they're exerting themselves, the higher their body temperature. Right? But obviously that's not going to be without restriction. Like if a person completes a mile in 6 minutes, that doesn't mean their body temperature is going to be 137 degrees. You know, it's going to be something reasonable. Right? You might see some minor fluctuations. So I'm going to go with 6.2, 6.6, 7.8 minutes, 8.1, 9 even, right on the money, 9.4, 11.1, 1, 2, 3, 4, 5, 6, 7. I'll get 3 more values in here. 11.3, 11.5, and 12.1. And I'll get all that in the calculator in a minute. Now let's say the body temperature, 99.1, 99.1 again, 98.7. Oops, that would have been bad. 98.8. So I'm going to get a little fluctuation going there. Back to 99.1, 98.6, 98.2, 98 even, 97.5, and 97.1. All right. All degrees Fahrenheit. All right, so I'm just going to kind of take you right down the list. Again, I said to construct a histogram for each data set. Yeah, you might just want to go box plot, just to keep it simple. Right, it's easier to graph, and yeah, we're using it to find outliers anyway, so why not, right?
Now, when we do this on like Google Excel, or do we draw it out? Or?
It's up to you. I'll just leave that up in the air. I'll do this again with Google in a few minutes, but I don't want to force anybody into a particular way of doing it. So if the by hand approach makes sense to you, then just do it that way. All right. Just when you make your graphs, just try to make them as neat as possible. That's the whole thing. That's one of the reasons why we go technology, is because you'll get a nice looking graph out of it. What some people have done in the past is they have used the online Numworks and just taken screenshots of the graphs that are on there. You know, so kind of like a mixture of, I'll do a little bit by hand, I'll do a little bit with the technology. You can go that route too. All right, so I'm going to go to, so we need mean, median, mode, and standard deviation. The issue with the regression app is it's only going to give you the mean and standard deviation. It doesn't give the median and the mode. So I'm going to go into statistics. I'm going to type in my X variable. I'm just going to ignore all of this stuff for now. I'm going to pretend it's not there. This first variable is my X variable. The second one is my Y. All right, so I'm going to look at just the X variable here, 6.2, type it all in, 6.2, 6.6, 7.8, 8.1, 9, 9.4, 11.1, 11.3, 11.5, and 12.1. All right. Double check. I did have a student try to see the amount of time that a person takes to accelerate when the light turns green. Like they're at a stop and the light turns green, how long did it take the individual to start driving? All right, and they did that, over the course of a few days, like day 1 this, day 2 that, and so on. Just to see, because they were looking at the distraction part of it. I mean, I can't get through a single day anymore without having to honk at somebody at a red light. So that was the thought there. All right, so I'll get those values in. I'm not going to worry about the second column yet. I'm just going to go to stats. I need the median, but I also need the mean, so I'm going to say X bar. I'm going to label S with a little subscript of X because I'm referring to the X variable. I need the median, and I need the mode. You put it in any order you want. I tend to do the X bar and the S first because in a lot of ways when dealing with quantitative information, those are usually the more meaningful ones. Right? The median, though, is 9.2. Go down and grab there's 2 things that say mean. I want the sample mean because this is not the time, like all possible times that one would take to run a mile. Like it's just a sample of 10 values. So we would use the sample mean 9.31. Sample standard deviation 2.124. And I made up the data so I knew when I was doing it that I didn't have a mode. All right? None of these values in the X column repeat. So I'm going to say none. And again, we talked about this last time. Like, you don't write 0 because when you write 0 as the mode, you're saying that's the most common number, and there's no 0 in this data set. All right? So I have this information. Now what I'm going to do, so that checks that box. Like we have to come up with a graph, right? So that's the next step here. The graph, again, I know the handout says histogram, but I would do a box plot. All right, so box plot, it gives you the scale, and it gives you all the important values on the scale. So I regret saying histogram to begin with, because this is a better option. All right, so I'm just going to do a quick sketch of it. Now this app straightens my lines out and makes everything look nice, so like if you want to do it that way, that's fine. If you have a steady hand when you do it on paper, that's fine too. Otherwise, just do a quick screen grab, whatever device you're using, and just pop this right in there. Just put it in a file and then put your handwritten stuff in that file too. I leave it up to you. All right. I don't want people to get bogged down in the technology. It's more like, can you carry out the process and draw a meaningful conclusion? 10, 11, 12, and 13. I don't really need the 13, but I'll put it in there anyway. Good thing about the calculator here, even more so than like Excel or Google Sheets, like this calculator is designed to give you the best fit for whatever statistical graph you're using, right? So it'll give you the perfect window. You see the little orange thing there? That's indicating what value you were on, which is 6.2. So I'm just going to ballpark it. That looks like about 6.2. The next one is 7.8. Going to make a vertical there. Then 9.2. The end lines, those should be a little bit shorter. Although in Numworks they keep it around the same, so I guess you can go either way with that. So 9.2 would be the next one. 11.3. I don't need the actual values. I just need your numbers to be placed where they're supposed to be placed. And then the last one, 12.1. All right, so I put a box around the middle three, or at least connect them. My app shades it in, which I guess is kind of nice. And try to make your whiskers somewhat symmetrical. Not symmetrical, on the same level. Because it'll be symmetrical or not based off of the data. Now this one looks like it has a little bit of skew, but I'd say it's generally roughly symmetrical. Right? In case you were wondering. There's no outliers. All right, I know there are no outliers because I have it set to display outliers under settings. If it doesn't display, if you have it set to display outliers and it doesn't actually display outliers, the calculator didn't do anything wrong. It just means your data set does not contain any outliers. All right, so that part's easy. So then we just got to do that all again for the y variable. All right, so I can overwrite the values that I have here, or I can hang on to them. Really doesn't matter. I'm going to wipe them out before I change my mind. So 99.1, I'm just going to start typing them in twice. 98.7, 98.8, 99.1, 98.6, 98.2, 98, 97.5, and 97.1. Oh, that's not a 1. Double check. Probably missed one along the way. I usually do. It looks like I got them all. All right, so we're just typing in all our y variables. I'm sorry, our y variable, the data contained within that set. All right, so instead of x bar, I'm going to say y bar. Instead of sx, I'm going to say sy. Still looking for a median. Still looking for a mode. All right. Go to stats. The median, 98.65. There is no y bar. All right, that's one of the unfortunate things about calculators, is that it doesn't understand the context. I wanted to find the sample mean for the y variable, so I would call it y bar. It's still going to call it x bar. It means the same thing because it doesn't know that I chose to call this column y. All right, so 98.42, so 0.704. All right, not a whole heck of a lot of variation. On average, data points have a deviation of about 0.7. You know, if you think about like human body temperature, assuming 98.6, usually 98.4 sometimes. If you're talking about a 0.7 degree in either direction, you know, maybe that's maybe a little bit of a fever going on, but I doubt it. Right? If you're ordinarily, let's say 98.2, and your temperature comes back at 98.9, you're not thinking that you're sick, you know. But if you're ordinarily 98.5, for example, and you're at 100, I mean that's a substantial difference. All right. The mode, 99.1. And that number occurs 3 times. All right. Again, I'm not asking you to state how many times it occurs, just what it is. But it's interesting information. Or at least it would be if I didn't totally make up the data set. Doing a box plot again. This one is showing a pretty significant skew. The box itself is displaced all the way to the right, and it feathers off, it tails off to the left a little, substantially, right? Scale wise, we could use their scale or we could change it up. It really doesn't make a difference as long as you get it on paper or, digitally. So I'll use their scale, 96.8, 97.2, 97.6, 98, 98.4, 98.8, and 99.2. And again, I'm just going to take their numbers and do the best I can to approximate location. 97.1 is going to be a smidge to the left of 97.2. Then we have 98 even. Then we have 98.65. All right, so that's going to be somewhere in this neighborhood. And then 99.1. So that one's interesting because it's telling me that the upper quartile of the data and the maximum are the same number. And also, and probably most importantly, I don't see any loose points. I don't see any points that are kind of off the beaten path, separated from the rest of the graph. So we would say also in this instance, no outliers. All right. If there was a disconnected point, you would report what that point is. Right? Just like I did before, I put in a 200. When I scrolled onto it, it said, it was a disconnected point and it was valued at 200. I would say there is an outlier when y is equal to 200. All right. It's also possible you could accidentally incorporate like unrealistic values. Like if I'm talking about human body temperature and it comes back with 200, it's probably a mistake. Right? So those instances you would just disregard. All right, if it's not possible, you don't include it in the data set. All right, now two variables together at the same time, we go to the regression app. All right, and that's just a kind of a rehash of what we did before. So I'm going to go out of here into regression, and I'm going to put all this data in again. All right, there is a way to port it over. It's just a little complicated. So it's not a lengthy data set. So, and I just want to remember, I typed this up and then I forgot everything I wrote. Oh yeah, you could change where it says under data collection and analysis, you must have a minimum of 30 sets of values. You change that to 10. All right, so minimum of 10 values. All right, so 6.2, 6.6, I'm just typing it all in again. 9, 9.4, 11.1, 11.3, 11.5, 12.1, 99.1, twice, 98.7, 98.8, 99.1, 98.2, 98 even, 97.5. Yeah, data entry is not fun. And this is simple raw lists of data. I have 30 values, 100 values, whatever. Like most of the time when you do statistical analysis in the real world, you usually have a device that collects the data for you. So if I'm talking about the speed of a moving object, I would use a device that measures the speed and automatically ports it into a spreadsheet for me. Right? So we try to avoid the data entry part of it in favor of the data analysis. All right, so we go to graph. This data set looks like it's all over the place, but I'm seeing a little bit of a curve there. All right, I see it's kind of going up and then going back down. All right, but you may not see that. You know, I kind of look at it like, all right, if I blur my vision, what kind of pattern do I see? You might look at it and say, oh, that looks like it's a natural loft. You know, it's level first and then it's dipping down. You might look at it and say, I don't see a pattern whatsoever, in which case just go with a line. If you see something discernible, go with that. But if it's not obvious, then take a step back and see what's going on. The default setting is a linear. So it gives us the correlation coefficient for a line if we wanted to use that as an option. All right. So I'll show you two of them. And again, the graph part of it, scatter plots could be a royal pain. Just screen grab it. That's what I was saying before with the box plot. Just do a screen grab if you don't want to do the by hand stuff. Because I just need something that's going to show the overall pattern in the distribution. I don't need the middle school, right? Can you plot points, X, Y? It's overkill. So I'm going to go with, I'll start with a line. I like to do a line to start, just to give a basis of comparison. All right, so what does a line give? And then from there, can I beat that? All right, so this is my line. It looks like it's missing a few points, but I don't see anything that's very far away vertically or horizontally. So I don't think there are any outliers between the two variables. So I have, for a line, y equals negative 0.295 x plus 101.162, and that has an R value of negative 0.889. All right, so that's my basis of comparison. At a minimum, I have a line. Now I want to see if I can do something a little bit better. All right. Again, no outliers or influential points. All right. And in the case of an outlier, it would be pretty obvious. It'd be like all the data points are grouped in one area, and this other point is like up here or way down there. Influential over here or over there. All right. Very far away from the overall trend of the data. All right. So we got the correlation of the line best fits data. I want to see, again, if I could find a better option. Now, I'm kind of seeing something that looks like it could be part of a parabola. Right? It doesn't have to be the perfect U shape. It could be just something generally parabolic. You could also make a case for a natural log. Kind of has the same structure in the short term. Really, it doesn't matter what you go with as long as you suspect that it might make sense in the context of the problem. All right. So I'm going to try. I was already there. I don't know why I X'd out of it. Let's go with, I'm going to try the quadratic. Oh, that looks pretty good. Right? If I look at all my points there, it looks like that parabola is just kind of hovering around the points themselves. So yeah, it's a little bit level here, then decreasing, and all the points are just kind of hanging out, almost as if they're attracted to the curve. Right? And you could go by the image, but you could also get the R squared value. Now remember, this is the annoying part. for a quadratic, and actually for a bunch of the other functions, sometimes they just give you the r squared, 0.903. You would then need to take the square root of that to figure out what the r is. All right, so I'll just do it separately. I don't have to go back and forth. Turn sideways. 0.903 square root, so about 0.950. All right, that's much better. I mean, it's almost like the same breakdown as the previous example, except this time I'm using quadratic. All right. Now, if you're satisfied with that, you can stop and say, okay, well, what's my equation? It's here. It's not pretty, but we can get it down. Y equals negative 0.0718 x squared, then plus 1.0262 x. I'm going to move this for a sec. Then plus 95.383. All right. So that looks like a much better option. I mean, both visually and also by the numbers. But if you're not satisfied at that point, I mean, if you want, you go right down the list. Try every one of them, okay, until you come up with the one that has the best R. But it's nice when you have something that's kind of a marriage between the appearance and also the numerical values. So I'm going to put a star next to the one that's the winner, little asterisk. All right, that's my winner. And then I say to make a prediction based off of the values. So find the line that best fits the data set and use it to make a prediction. So I'm going to predict, and it really, you can pick whatever you want, as long as it kind of makes sense in context. I'm going to predict the body temperature, body temp of a person who runs 1 mile in 4 minutes. Yeah, because the lowest I had was 6.2 minutes. So I would go to right on down the line. And I can tell you that the computation without this predict function is kind of brutal for some of these models, whether it's exponential, log. The fact that it does it for you in Numworks is actually really nice. So you would have, if I put in a 4, 98.34 degrees. So 4 minutes, 4-minute mile corresponds to 334 degrees Fahrenheit. Now, I don't think we drew any kind of earth-shattering conclusions here, but according to this model, that's what we would be looking at. And again, if you decided you want to go with the line, you come up with a different outcome. I just need to be able to put your data into my calculator and come up with the same outcomes. Right? Same mean, same standard deviation, everything along those lines. And then the conclusions, the last little bit, conclusion. What conclusions can you draw about the relationship within and between the two variables? I put the little requirement of 500 words. It's basically like a paragraph and a half. It's not anything too insane, and it doesn't. I'm not counting words, right? As long as you get the idea across. What I'm saying when I say 500 words is, don't just give me a one-line answer. Elaborate. It does not have to be a full-blown essay, but it should have a little bit more than, as temperature increases, the speed, the time it takes a person to run a mile decreases, or like, no, a little bit more than that. Incorporate some of the other details. And in fact, if you just want to do a recap of all the data that you crunched out, all the summary statistics, and say, The first data set, which was time it takes to run a mile. So in the case of the time it takes a person to run a mile, on average, that person will complete that in 9.31 minutes with a standard deviation of 2.124. Whereas for temperature, we're looking at a mean of 98.42 degrees Fahrenheit with a standard deviation of 0.704, showing that the data for the temperature is more compressed than the data for the time because the standard deviation is smaller. Things like that, right? Talk about the shape of the distribution. So in my box plot for for time, it was approximately symmetrical. For temperature, it was skewed significantly. Right? So these are some details that you can get into your write-up. Again, I'm not asking you to fill out a page of paper front and back, and I honestly don't have the attention span, but you gotta hit all the salient points along the way, and if you do that, you're good. Right? So this is actually, I'd give this if this was submitted to me as is, I'd give it a C because it doesn't have the conclusion. But assuming a well-written conclusion along the way, this is an A response, right? So if you do something like this, you're good, right? I don't want to hold you up. We could do it on Google Sheets now, or if you're comfortable with this, we could just go this route. I could just show some people how to do it on Google Sheets if you want, or make it optional. But I don't want to hold everybody up because I know some of you need to finish your budget project, and then also on top of that do this. So yeah, that's what I'll do. All right. So I'm gonna call it an end right now. And if you want to stick around to learn about the Google Sheets approach, I'm happy to do that for you. But yeah, I'm not going to make everybody stick around just for that. All right.